I'd like to thank Mike and Mike for the kind invitation to this wonderful conference. And so I guess the purpose of my talk is to share my enthusiasm for Ricci flow as an interesting subject and to encourage kind of the communities of Ricci flow and machine learning to connect more with them, and actually to pose a question to the machine learning community, what we, people in Ricci flow can do to kind of help, foster this more interaction. Okay, so I'll just give a very broad overview. I feel like this is, there's a lot of pressure. I feel like this is an interview. So I think that was a very apt Freudian slip. But whether it's interview or overview about Ricci flow, I'll give that. And then at the very end, I'll just pose some questions. And in fact, these probably might be the wrong questions. So the question is, what are the right questions I should be posing? So, but I was told by a well-known criminal lawyer in San Diego that never answer a question with a question. Apparently, that's high-profile politicians have done that. It has not served them well. Okay, so let's see if I'm a doofus at electronics. I'll try to make sure I know left and right. And, I think this should work.
Sometimes it doesn't work, and sometimes it requires.
Oh, okay. It was working earlier. I think I did something to destroy it. So. Pardon? That's what I usually do when I go online and ask for help. Ask, is it turned on? I say, oh.
Okay. The arrow keys work on the. Try
okay, I'll try that. There.
Clicking on the slide.
Yeah, click on the window. It's on.
With the pad on the bottom. The trackpad.
Well, I mean, we can just. Oh, wow! Something happened there. Which one was that? Oh, okay, wonderful. Okay, okay, wonderful. Okay, so shall we begin?
Yeah.
Okay, so it's a general question we're posing, and so the idea is that Ricci flow has actually climbed to great heights, and the most famous works are due to the creator of Ricci flow, Richard Hamilton. And he developed over many years, about 2 decades, a very detailed program and very convincing program toward Ricci flow. But then many unresolved and very deep problems remained. And it looked very close, but in fact, there was a lot of very deep problems, and these were solved by revolutionary insights of Grisha Perlman. And since then, now we're more than 20 years later after Perlman's work, I would say led by Richard Daimler, there's now hope for understanding Ricci flow well in dimensions 4 and above, and especially in dimension 4. And as is well known, there's a long history of continuous and smooth 4-dimensional topology. And the question is whether Ricci flow can contribute to that. And toward that end, there's the famous 11/8 conjecture, which would be the remaining step in solving the question of which simply connected topological four manifolds are smoothable, that is, emit smooth structure. And actually, back around 6 or 7 years ago, Mike Friedman suggested the idea of Ricci flow as an approach to the 11/8 conjecture. And the thing I also want to mention is that, and maybe this is on the later slide, but it looks like from the work of Bamler that understand, and others, especially Muntiano and Jiaping Wang, on understanding Ricci solitons, it looks like that perhaps one can even consider the possibility of a geometrization conjecture in dimension 4. Okay, one aspect of Ricci flow in recent years is getting more abstract with Bamler's work. This seems like a necessity, and the reason is the Ricci flow is something that takes an arbitrary metric on a closed Riemannian manifold, and it deforms it, and it's a nonlinear heat-type flow. And so singularities must develop. And it turns out that one should kind of consider the notion of Ricci flow in more generality. And it looks like Bamler has found the right notion or is very close to the right notion in his notion of metric flow. So it's more like metric spaces or metric measure spaces. Okay, so I think the main thing is today I only give a very small glimpse of Ricci flow. Okay, so I don't know if this will work. I'm afraid to play this video. And if I go to Safari, I probably won't figure out how to go back. Okay, so let's not do it, but just maybe I will kind of take a, like this. That's our surface. Okay, that's our initial one. And you can kind of imagine it kind of deforming. It's like this incredible balloon, misshapen balloon. And it starts to, like, if there's something like this, it'll expand like that. And these are snapshots or stills from a movie, right? So on the very left, you have the initial metric. And it's a smoothing process. And this isn't 2D. This is a 2D picture, not higher dimensions. So something very different happens in higher dimensions. And so what happens here is you see a kind of a thin neck here. And that will actually, in 2D, that has only negative curvature. And what happens is when you have negative curvature regions, they expand. So they'll expand like that. And eventually it'll be convex. And then it'll shrink, but this doesn't show it, but it'll shrink to a round point. So the geometry will become asymptotically spherical. And what happens is for Ricci flow in general on surfaces, you always converge to constant curvature. Okay, and so there are many successes of Ricci flow, most notably the Hamilton-Perlman proof of the Poincare conjecture, and much more generally, the Thurston geometrization conjecture. And in recent years, in the last few years, there's been also another spectacular breakthrough of Bamler and Kleiner proving the generalized Smale conjecture. And there are other well-known conjectures in geometry. One of the famous conjectures is the quarter pinching conjecture of Brendle and Shane. So I will not go over the details of these results, just to kind of note some very impressive results have been done over the past few decades. And but one of the things in this talk I want to emphasize is that due to Richard Bamler's work, there is a program to geometrize four manifolds. Okay, so like for Ricci flow in 3D, it meshes very well with the topology, right? So you have the prime decomposition of Naser and Milnor. Milnor, and then you have the torus or JSJ decomposition. And what happens is Ricci flow affects those decompositions in finite and infinite time, respectively. So the prime decomposition is affected in finite time. Superfluous surgeries can happen. Like you can kind of bubble off a sphere, right, topological sphere. And so the new manifolds are two of them, one diffeomorphic to the original three manifold, and then another is a standard three sphere, and then they're connected, sum is the original three manifold. Okay, but even with that, you could say that I would characterize it as saying that Ricci flow satisfies topological monotonicity in every possible way, except that sometimes it's like monotonicity means staying constant, right? And then the torus decomposition happens in infinite time because what happens to the non-collapsed pieces are necessarily hyperbolic. Actually, that's a very simple calculation from just the evolution of scalar curvature. Okay, so you could get something very important, that means hyperbolic pieces, from a very simple calculation. And then the rest is collapse, but then there's a Cheever-Gromov theory for that allows, well, it means there's F structures and therefore it's hyperfibered spaces. And so, well, the takeaway is that Ricci flow can prove geometrization by the Hamilton-Perlman theory. And you don't actually affect the geometric decomposition exactly, you infer it from the infinite time behavior.
Ben, can I?
Yes.
Just as sort of a question and a comment, in going past dimension 3 into dimension 4, and maybe the audience can think about this during your talk, but there are logical issues, right? Because there's no algorithm to tell whether a manifold is simply connected beyond dimension 3. So I'm just wondering if Ricci flow did all these great things in higher dimensions, whether it would contradict something in logic, whether running Ricci flow would enable you to tell whether a manifold is connected by watching its prime pieces.
Right. So the idea would be that there could be a geometrization theorem, but it's very hard to infer topological results. So kind of in 3D that happened, right? You well, not exactly immediately, but you infer those this whole plethora of topological results. But what could happen is you can imagine geometrization being true, but the sense is true, then you cannot infer topological, but except maybe for 11/8, because second Betty number and signature are cobordism invariants, et cetera, right? Because kind of they're very coarse invariants.
But you might lose the fundamental group through some singularity and never know what you started with.
Yeah, I mean, it's something you told me earlier, much earlier, that you could take a standard S4 and you can take a 2-knot. So for example, spun 2 knots, right? And so that means the fundamental group or the knot group would be the same as the knot group of the 1 knot that is spun of, right? And then you can, I believe that there should be a surgery that affects a 2 surgery on that. So you can start with S4 and then effect a 4 manifold whose fundamental group is any 1 knot group, which would, so there you lose all, I mean, in a sense, you would think that you lose topological monotonicity. It's very different than 3D. But the idea is that, per your suggestion, is that for the 11/8, maybe you have this type of monotonicity because you're just looking at the ratio of the second Betty number to the absolute value of the signature. But even then, it will not be monotone. And so kind of the one thought is that geometrization should be what the flow decides. Okay, so that's one philosophy one could take. That whatever the surgeries that Ricci flow effect, those will be the surgeries one should do on a 4 manifold. Okay, so those will include 2 surgeries and 3 surgeries, but not 1 surgery. So that's for a geometric reason. And the reason is a curve has no intrinsic geometry. And so that's why you don't see 1 surgeries. And that's the same reason you don't see 1 surgeries in 3D. But 2 surgeries and 3 surgeries should occur.
Just brief question. I've heard talks about this in the context restricting to Taylor manifolds. Do you think that's a simpler context?
Yes, I mean, I think there's a lot of work of that. Then there's a Song and Tian program to approach through Taylor-Ricci flow, the minimal model program. Yeah. So I think maybe in 2 complex dimensions, maybe that's close to, I mean,
So yes.
well, I mean, it's still very difficult even in 2 complex dimensions, but maybe that's on the horizon of being resolved. But then even more interesting would be 3 complex dimensions. But they have a whole program
Thanks.
there. And, okay, and one thing is I think really remarkable about Ricci flow is that it synthesizes a geometry analysis and topology. So sometimes you can look at an argument and you can't even tell whether it's geometric or analytic. It just has, you know, facets of both in such a way that's so well synthesized. And so it's quite remarkable. And that was done to a high level by Richard Hamilton, I feel, but it's brought to a much higher level by Perlman. It's just kind of things you didn't believe were true. That means a kind of a mindset throughout the history of geometric analysis is always to put curvature conditions to obtain Bachner formulas. And so what was remarkable was that Grisha Perlman proved monotonicity formulas. That means like a Lyapunov function. You think of a dynamical system. And that he proved that without any curvature condition in all dimensions. And that was like, that was a mindset that you wouldn't believe would be true. And and then he tried to justify it, you know, various ways by going to potentially infinite dimension and certain adiabatic limits. But it's kind of unclear why you could maybe use some physics cliche why Ricci flow is unreasonably effective, but it seems to be. And one thing is it has applications to topology. That's one of the main applications you seek for, right? You seek, there are applications in geometry also that are very important. But looking at speaking to topological applications always seems to be like a holy grail, you know, in the subject. And but the use of topology is kind of rare. That means using topology to study Ricci flow is rather rare. I mean, some exceptions are the fundamental group, and also homology and cohomology can be used. So that was some work that Mike, myself, and Shin and Zhang did, where we're able to use a algebraic topology argument to prove an analytic estimate, and that goes through so-called ALE exclusion, which was probably first studied by Mike Anderson, and that result uses a very deep theorem of Cheeger and Neighbor. And so that's actually another question that this field relates to many different subjects, and one possible direction is to have it more synthesized with the Cheeger-Colding-Neighbor theory, and that's done to some extent by Richard Bamler, but there's much more on the horizon, presumably. Okay, so kind of the takeaway is that Ricci flow is connected to many different subjects, and that was especially apparent by the work of Perlman. Okay, this is a little bit in reverse order. So this is background on Riemannian metrics. So the takeaway from this slide is you want to say that Riemannian geometry is kind of the simplest possible generalization of Euclidean geometry to a nonlinear manifold setting. I mean, you simply just take, infinitesimally what you see is a tangent space and there's an inner product, right? That encodes, angle and distance. And you just have it smoothly vary on your manifold. What could be simpler? And of course, there are lots of manifolds. I mean, these are one of the many, many examples. The only reason we mention these is cylinders in particular are one of the prototypes for singularity formation. So we saw like a dumbbell shape, but in higher dimensions, things can pinch. So you can kind of imagine if you zoom in on where a dumbbell is pinching, you take an infinitely powered microscope. So how do you do that? You take a sequence of finite powered microscopes where the power goes to infinity. And then you take a Cheeger-Gromov limit, or more generally, you could take an F limit in the sense of Bamler. And what you see is sometimes a cylinder. Okay, and this in 3D that really related to the prime decomposition, the connected sum decomposition. Okay, so those are just pictures rendering that information. And then the idea is that once you have the Riemannian metric, this infinitesimal notion of distance and angle, everything falls out naturally. So the Levi-Civita connection for parallel translation, there's a unique, metric compatible torsion-free, linear connection. And then you can talk about how non-commutative covariant differentiation is, and you get the Riemann curvature tensor. And so the Riemann curvature tensor is a 4 tensor, but the metric tensor is a 2 tensor. So what you can do is you can average curvature. So the notion of averaging curvature goes with the trace. So you basically take a trace and you get the Ricci tensor, and then you can take another trace and you get the scalar curvature. Okay, so one of the remarkable things about high-dimensional Ricci flow is that somehow in the development of theory of Perlman and Bamler, that the full Riemann curvature tensor is not used so much. It doesn't really appear in analysis. And you would think that it should, right? Because when you start with a metric Levi-Civita connection, the first thing you get is Riemann curvature tensor. And so, so it's kind of a mystery how come the full Riemann curvature tensor doesn't really appear so much in analysis. It's almost absent. I mean, you could argue that, well, you need that for Cheeger-Gromov convergence, but still, it's rarely used. And that's very fortunate because the heat type equation that satisfies is very complicated. And that that's one of the reasons this work of Brendle and Shane is so remarkable, because they had to deal with that complication of the Riemann curvature tensor.
But more than Ricci is used, right? If not the Riemann tensor per se.
That's the crazy thing. No, that's, I mean, well, you can, right, if you do quarter pinching, but in the Perlman Bamler theory, no, that's the remarkable thing.
In all dimensions.
Yeah, I mean, even in 4D, like what we did with Mike and Shin and Zhang, the moral of that story is that if you can control scalar curvature, you can control Riemann in 4D. And the reason is ALE exclusion. What happens is if you're trying to get estimates for singularity models, you're taking sequence of points going up to infinity. If you don't have scalar curvature controlling Riemann, then you pop out an infinite or infinite sequence of ALEs in your singularity model. Now, the point is the singularity model is the singularity model of a closed form manifold. So what you get in the original closed form manifold that you're studying Ricci flow is an unbounded number of disjoint ALEs, at least topologically diffeomorphic to. And then there's a contradiction. It also, not just homological arguments and Perlman point picking, but it also uses some index theory with Hertzberg signature theorem and Chern-Gauss-Bonnet. But you put all that together, then you can obtain that analytic estimate to that topological argument as I alluded to. But the takeaway is that scalar curvature controls Riemann. So, yes.
Yeah, there's, as you know very well, this comes up in physics with this beta function of the sigma model, and there's this intuition which I find helpful, maybe you can comment on, to say that Ricci is the local variation of the volume form.
Yes.
Yeah. So
Oh, okay. So the thing is, volume is just remarkable, insanely important in Ricci flow. So even entropy, I think Perlman is trying to interpret it as volume. So like everything is volume in one way or another.
you just need to know Ricci to control the volume.
Yeah. I mean, and that's along directions, but even if the volume, you look at the volume form in time, you only need to know scalar. And so what happens is a lot of the work, you don't even need to know evolution of Ricci. You need to know evolution of scalar, and Ricci is on the right-hand side of the equation. And we'll see these things in detail. Okay, so Thurston's idea was to decompose into geometric pieces. Of course, the constant curvature, products of 2D constant curvature R, and then, SL2R, nil, solve, and all that. And so there are 8 geometries, and we already described how things get broken up. And so that's the statement of Thurston's geometrization conjecture. And so the idea is, it looks like in 4D, Ricci flow could give a geometrization program. And so we want to say a little bit about how that might be. Okay, so I've been talking about Ricci flow. We never even said what the equation is. It's like this. And Hamilton has famously said, and when he first started out, he didn't know what he was doing, so he put a plus sign there, right? Because we always first prefer positive to negative. But then when he did calculations, he saw that it's working like a backward heat equation. Okay, so one of the remarkable things about Ricci flow is that it's really immensely like the heat equation. And so when you compute geometric invariant, you see heat equations popping up all the time. Okay, you cannot see that from this equation, right? Maybe if you knew that in harmonic coordinates, the Ricci -2 Ricci tensor looks like the Laplacian of the metric plus lower order terms, yeah, then you can see that. But just looking at that equation, you don't see it. But when you look at evolution of scalar, we'll see that you'll see it, actually see the heat equation in a very simple, essentially semi-linear form. Okay, so what do you need to know? You need to know that if you start with any initial metric, you can move for a little time, right? Because otherwise you can't use it as a tool. So you need short time existence. That's true. That's proved by Hamilton using Nash-Moser, and it was much simplified by Dennis de Turck. So the idea is Ricci flow is not exactly parabolic, and the reason is exactly because it's diffeomorphism invariant. So that creates zeros in the symbols, in the symbol. And de Turck was able to break the diffeomorphism invariant and show that it's equivalent to a strictly parabolic equation, and then you can use the standard theory. So you get short time existence. So now you can use it as a tool and run it a little bit. And the question is, does something good happen for any initial metric on a closed Riemann manifold? And the remarkable answer is yes. Okay, so you take any closed Riemann manifold and you take any Riemannian metric on that closed Riemann manifold, then something good would happen. That was proved by Hamilton and Perlman, and that yielded the geometrization, a proof of Thurston's geometrization conjecture. Okay, so it's not, you're also not just using Ricci flow, you're using the Cheeger-Gromov collapsing theory, as I mentioned earlier. So you don't have to go to a generic metric or something. It's not like, okay, most metrics are good. In a certain sense, all metrics are good. And then, of course, the question is that true in 4D? And nobody knows at this point. Okay, so kind of the idea with Ricci flow is, well, it's a nonlinear system of equations that's geometric, right? So it should be very hard. Okay, but because it's on a manifold, a lot of techniques for PD either don't work or it would be very hard to get to work. And so the fact is that the techniques in Ricci flow are actually very rudimentary often, at least at the foundational level. That means they're very specific and elementary methods that work because those are the methods that work on manifolds. And the first thing is the first and second derivative tests. And so what does that mean? That's just the maximum principle. Okay, so what's the idea? The idea is we're going to see that under the heat equation, like what happens if we're at a given time and we're at a spatial maximum? As we go forward in time, what wants to happen? Well, at the maximum, Laplacian is non-positive. And so, but the Laplacian is a time derivative. So that means the time derivative must be less than equal to 0. So the maximum wants to drop. And that's how we get in. This very fact gives us an a priori estimate for a solution to the heat equation, right? The maximum wants to decrease. And that's all it is. Okay, but the idea is this can be applied in many different ways and in some very, very clever ways. And that's what I just said is this is the context of this next statement. And the idea is it also works if we add in a kind of a drift term right here. Put it arbitrary vector field. The smoothness of the vector field doesn't really matter. These things you have to often prove it rigorously by a fudge factor at epsilon, like ramp it up or ramp it down and all that. And so it's true under very general conditions, and there's hardly any conditions on how G of t depends on time even. But we'll apply it to where G of t is a solution to the Ricci flow. Okay, so we talked about the heat equation. There it is, the heat equation for the scalar curvature. It's exactly the heat equation. Of course, the metric is moving, so Laplacian with respect to a moving metric. And then you have this nonlinear term, but the nonlinear term is non-negative, which is really good. So it's very good for getting lower curvature bounds, but very bad for getting upper curvature bounds, because that's quadratic nonlinearity. And you could even say this is big equal to 2 over n times the scalar curvature squared, where n is dimension. Okay. And so in particular, if you have a lower bound of the scalar curvature, then that's preserved under the Ricci flow simply by the first and second derivative tests. And then how do you get that equation? Is standard variational formulas. And then you take a variation of metric and calculate the variation. And then you could take that variation to the Ricci tensor. And then out pops the formula. You use second contracted Bianchi identity, some standard identities. And that's how you get your answer. So I won't go into the rest of the slide. Okay, now the point of this slide is that, of course, the scalar curvature is the tip of the iceberg, right? In terms of quantities you can control. One of the reasons that Hamilton could prove his famous theorem that at the very beginning in '82, that positive Ricci curvature, 3D, means topologically it must be a spherical space form, is that he could, as you go along the flow, you have some measure of control of the geometry. So that's the art of the a priori estimate. Like, what do you control? And so there's so many possibilities. And he found out it's a very simple thing. One of the key estimates, of course, there was a lot more work to be done there, is to control more complicated curvature tensors by more elementary, right? So the idea is in 3D, the Weyl tensor is 0. So the Riemann curvature tensor can be completely recovered from just the Ricci tensor. So that's one of the simplicities of 3D, is that you only have to look at the Ricci tensor. And so this is a fundamental estimate. The scalar curvature is tracing, so you lose information like that. And so you're bounding something more complicated by something more simple. And it's like a uniform estimate. C is uniform in time. Now, the maximum principle, a little bit more complicated. So one of the nice things that Richard Hamilton developed was a maximum principle for systems. And there's some precedents for that, like, for example, due to Hans Weinberger and all that. But what this meant is that you sometimes can control the full curvature tensor or the Ricci tensor, Riemann curvature tensor, if you get nice equations. Okay, and 3D is particularly nice. And what this says is the following. So I'll kind of skip this part and kind of go to the key consequence is that means when we look at a singularity model, that means what is a singularity model again? It's when we zoom in with this infinite power microscope, as the curvature goes to infinity at a given time when the singularity forms, and we see a limit, right? We see an idealized picture. And these singularity models are on, well, you do a blow-up process. So the fact that the microscope has a infinite power means that the limit is often non-compact. And all these singularity models, whether they're compact or not, they have non-negative sectional curvature. That's a very strong condition. So for example, a well-known theorem in Riemannian geometry is that manifolds that are complete non-compact with positive sectional curvature have to be diffeomorphic to Rn. So that's due to Gromov and Meyer. Okay, and so, but what happens if you don't have positive curvature and non-negative? Well, Hamilton had a strong maximum principle for tensors, which implied splitting. That means the manifold had to be a product of R and a surface. And so what happens is the effect of this so-called Hamilton-Ivy estimate is that the topology and geometry of singularity models in 3D are extremely simple. Okay, and this was what allowed surgery to occur, allow you to develop a surgery theory and prove geometrization. The fact that 3D singularity models are very simple, both topologically and geometrically. And then another application, another famous application of the maximum principle is Hamilton's trace Harnack. So what is a Harnack estimate? So it even goes back to like complex analysis, but these are all in the differential form. So they're actually gradient estimates. So the idea of a gradient estimate is a long history going back, like probably almost 100 years. But in geometric analysis, it was really affected by Yau. So he proved things about harmonic functions on Ricci non-negative. He did work with Peter Lee for the heat equation. And what was remarkable, Yau and Lee's work on the heat equation transplanted perfectly to Ricci flow, which is a nonlinear equation. So Hamilton first figured out this Lee-Yau type inequality for the Ricci flow on surface in 2D. And what he told me is one of the few things that he did, the first time he tried it, it worked. That's how, it worked exactly like the heat equation case, and that was remarkable. He applied it to the scalar curvature. But then he proved it in much more generality, and it had profound impact in the 3D singularity analysis. And this was incredibly complex. So that took many years to do that. And I think I'll kind of skip this for the most part. The takeaway is that Perlman's techniques and all that were like super refined. They're super sharp. As I mentioned before, that they did not have any curvature condition. And the reason is, one reason, possible reason, is that he kind of discovered a space-time geometry. That means you're not just thinking like, okay, it's Ricci flow, it's just metric dependent T. There's actually a space-time geometry there. And so there's the idea of a space-time distance. So it turns out that the important things in Ricci flow is to kind of understand that distance. And then he also another fundamental idea that he introduced that was actually occurred for other flows like curvature flow, harmonic map heat flow, and then Hamilton was actually even searching for these things, was looking at an adjoint heat kernel coupled to the Ricci flow. And that also was very much related to space-time geometry. And another aspect is so-called Nash entropy. So I won't go into these, but it turns out like kind of what is kind of the newest way to approach Ricci flow is through Bamler's use of the adjoint heat kernel. So it was begun by Perlman. He has this one estimate, but used to incredible effect by Bamler in recent years. So I won't really go into those things. And I think I'll skip these slides for the most part. So the idea is that Perlman had one of the Lyapunov functions he had, or monotonicity formulas, was the first one he has, and is for what he calls the F energy. And this appears in the physics literature as a low energy effective action. And there's probably many papers, including like Strominger and Vafa, when they look at the Bekenstein entropy of black holes. And so this was kind of a paradigm shift in Ricci flow. Hamilton coupled with the Ford heat equation, we looked together with him at linearized Ricci flow. But no one found or thought to think of to couple it with a single functionless equation. And this was remarkably synthesized with Ricci flow. That things suddenly became more natural. So it's kind of weird, like you put Ricci flow in a bigger system and Ricci flow looks more natural. So in particular, it was not believed to be variational, to be a gradient flow. And this completely changed it. This showed that in a certain sense, it was exactly a gradient flow. But you had to add F, which in the physics literature is called the dilaton. Now, the point here is to say that you can really think of this as kind of a riff on the Einstein-Hilbert action, or total scalar curvature. So the point is, when you look at the variation of the energy, variation, this is rather confusing. dV means the volume form, and V is something completely different by itself. It's a two tensor that you vary the metric in the direction of. So this is a very unfortunate notation. But this is a very standard formula right here, and that's right. You see the Einstein tensor. But from the point of view of the Ricci flow, you don't want that. You simply want the Ricci tensor, right? But if you think about it, the scalar curvature is second derivative metric. So as a partial differential operator, it completely changes the symbol. And if you flowed by the Einstein tensor, you would not have short time existence. And so Hamilton's solution was very simple. You simply throw away this term, ignore it, and just look at Ricci flow. But Perlman says, well, you can actually do a riff on the E energy and turn into F energy by adding this extra equation. So the idea is, roughly speaking, I won't go into the details, this term is due to the variation of the volume. So if you can make the volume fixed, you wouldn't have that. But you have to add a Dirichlet energy. Okay, so it's geometric and analytic at the same time, right? Can you determine whether it's a total scalar curvature or a Dirichlet energy? Depends on whether you think of as point of view of G or F. Okay, so, well, the main takeaway from here is that it works. And a key thing is when you have monotonicity. If F is monotone, what happens when F is constant? you find out this notion of a Ricci soliton. So a Ricci soliton is an equation that involves not just G, but also F, and it generalizes the Einstein equation. Now, this is extremely fundamental for Ricci flow, because what it says is that I have an object. If I try to move it under Ricci flow, it would not move. Well, it is moving because the evolution metric would be the Hessian, but it's only moving by diffeomorphism. See, that's another way to think of that is just a lead derivative of the metric with respect to grad F, and then say divide by 2. Okay, and the key takeaway I want to say from here is that there's actually a very important generalization due to Perlman called the W entropy, where he added a scale factor tau. And then everything that also had monotonicity. It proved so-called no local collapsing. This allowed singularities formation to be studied and all that. And so I will skip that, but that is a very fundamental now tool, the W entropy monotonicity. Okay, so there are other applications. I think for the sake of time, let's skip those. And kind of let's now change gears and think about how Ricci flow might fit in with topology. So very standard topological case surgery, where you take SK cross Bn minus K, and then you replace it by something that has the same boundary. That means you increase the dimension by 1 and turn it into a ball, and then decrease the dimension by taking the boundary to a sphere. And you cut out this product and replace it by that. So that will be a case surgery. And then this is a kind of a transformation of your manifold. And if you have a 1 surgery on the 2 sphere, you can see this will be what it is. Okay, so this is a very standard notion in topology. And the key thing that Hamilton and Perlman showed was that this happens in 3D Ricci flow. There's things called neck pinches that I mentioned. The singularity model is a cylinder. Now, one of the key features of 4D is that if we look at smooth manifolds within that category, we're forced into the category of smooth orbifolds with isolated singularities. Okay, so that's unavoidable. You have to go into the orbifold category. And the reason is very simple. What you could do is simply imagine a neck region in a 4 manifold where this center right here is a spherical space form. And that will pinch under Ricci flow because there's positive curvature, very little negative curvature in comparison going this other way. And then what you have is a singularity here. One of the S3 mod gammas pinches to a point. And then the idea is you can do a surgery. You can move this region right here and replace it by something like that. And topologically, it's shown how that happens. And then the key takeaway here is that now if we started with a smooth 4 manifold, we have an orbifold with 2 isolated singularities with isotropy group gamma. Now, there's more complicated things like degenerate neck pinches, and I won't get into this much, except to say it can be shown to exist by kind of a continuity argument. You take a 1-parameter family of initial data. On one side, you start with a singularity like a round 3-sphere or 4-sphere, whatever you like, whatever dimension, and then the others. And for the singularity that occurs for the initial data at the other side of this interval is a cylinder. Well, now a continuity argument will show that there should be something that interpolates between those 2 singularity models, a sphere and a cylinder. And what that is a Bryant soliton. So that means if this looks like a cusp, but when you zoom in under infinite powered microscope, that looks like a bowl. And so that's one type of surgery. And now there's another type of surgery where you can kind of imagine, because we're in 4D, so something complicated where you could have a singularity model S2 cross R2. And that could pinch like that. And this could be very complicated. The only thing I want to do is help you remember this. So this is kind of like blue and red. So it's like purple, right? And then you can kind of think of that as fire, and this is water. So this is like deep purple, smoke on the water. And this maybe we should call this conference geometry of machine head. Okay. Oh, I figured at least one person would get that joke because
I just didn't hear the word said again. Geometry of
machine head.
Oh,
Because I saw a deep purple T-shirt in back there. I should person who has to stand up if they're here. And so that's how you can. And this is kind of apt because when Richard Bandler explained to Mike and I about 6 or 7 years ago, he talked about a fire spreading and all that. When these are kind of two spheres pinching off the points. Okay, so that's how you can just remember deep purple. And then that's these. So, but the takeaway is that there are surgeries that generalize to surgeries, and they involve looking at surfaces cross S2. And so I'll just kind of draw pictures of this. You cut out this region, you cut out a certain region, you glue in something else, and that's the surgery. And this surgery generalizes to surgery. Now, why is this plausible? So the idea is that something like this happened in a certain sense in 3 dimensions. So Perlman has a standard solution which is asymptotically cylindrical, and it's used to do surgeries for neck pinches like that. And this can be adapted here where the standard solution will be crossed with a line because we're in one higher dimension. So one of the takeaways is, so why does Ricci flow work in 3D? Well, one of the reasons is dimension reduction. Okay, so that's a very standard theory in geometric measure theory. It's used in the Cheer-Colding neighborhood theory in Ricci curvature. But in Ricci flow, it's obtained by pointed Cheer-Gromov limits. But in any case, the point is that in 3D, singularity formation is simple because 2D singularity formation is very simple. Any singularity in 2D has to be around shrinking 2-sphere. And so by dimension reduction, certain singularities are S2 cross R cylinders. But now what happens is if you think about 4D, that's going to go down to 3D, right? That's going to build by dimension reduction. And so 3D is more complicated, and then you have to factor that in. So that's why the complication will, that's one of the reasons the complication will increase. And so this is a picture of surgery and use Perlman standard solution. And this is just a plausibility argument by picture of why this will work. The idea is in a surgery, you're looking under a microscope. So this is extremely small scale. That boundary of the surface, which is diffeomorphic S1, is extremely small scale. So this is almost linear. And so that's why something like that should be possible.
And I just want to make sure you get to the AI part of your talk.
Oh, okay. So I'm trying to avoid that. So you exposed me, right? Okay, so there's other surgery slowdowns, asymptotically cylindrical stuff, right? That generalizes. There's this wonderful theory I mentioned, Montagnier Wang, of solitons. And so the takeaway is that there's even more singularities. There's a BCCD thing that's on connected sum of CP2 and C2. And there's even more. But these are all very nice. So everything known is very nice. There's cohomogeneity 1. Solitons, we will not get into that. So solitons are self-similar. So under a microscope, if you look at it, when you take the limit, you get a movie. The singularity model is actually a Ricci flow. And by self-similar, it means it doesn't move if you factor in diffeomorphisms and scalings. And there's even something called the flying wing due to a Lie conjecture by Hamilton that works in 4D. There should be a notion of full boardism. Ricci flow will give you a full boardism. that generalizes that Bandler's program is about approaching 11/8 by trying to get monotonicity for this signature to Betty number ratio. It's not exactly that simple because of ALE formation, but it looks like it may be possible. So we'll just kind of skip all that. There's various reasons, sorry, it's like going through the various reasons why this is plausible and kind of from the moral perspective. So we'll skip that. And the long time existence is part of his theory. So it should be similar to 3D, except that instead of hyperbolic pieces, you get Einstein pieces. And so the key thing to remember is we're only trying to control very rough topological invariants, such as signature and second Betty number, which should have good behavior under flow boardisms as well as coboardisms. Okay. So, so the idea is that there should be a whole hierarchy of questions, right, from the most difficult and long-ranging to very specific. So the point is Ricci flow would be the something that has builds on things and this wonderful foundation, and then as long as you don't find out that Ricci flow is unmanageable, there's more and more hope as more and more theorems, right? And of course, the question is, can AI be part of that process? One of the things is that there are lots of expository works on Ricci flow, right? Because first of all, Hamilton was an incredibly clear writer and he had a plethora of ideas. And then Perlman had very dense papers, but then there are many groups of people that wrote long expositions of that. And so there's, like LaTeX files and all that. And so I would take the point of view that formalizing in lean could only be a good thing. And then so these are some people that are working in it. And then, I hope to connect more. I'm, trying to communicate with people there. Right now, the formalization is only at the very beginning stage of Riemannian metric and Levi-Civita connection. That's where it's at. But to me, at least for the foundation of the Ricci flow, it should be very elementary in a certain sense, although lean is very tedious and difficult and laborious. One shouldn't think that it's a particularly difficult field to try to formalize. And so another question we have is, what should we do for to help train AI in Ricci flow? We're starting work with Jingbo Shang and CSE at UCSD and Zilu Ma, Chen Yang, and Robert Corella and Peng Liu to create data sets for Ricci flow. And by the other hand, since I'm a complete neophyte, we don't really know what's best, and that's a question for the audience. Would it be better to annotate LaTeX files, for example, for Ricci flow books for training? And there's just certain things about what to formalize and what generality and other things to formalize here. And there's specific questions. So there's many, many open problems in Ricci flow, various levels of detail. And the question is whether AI can help with that. And even specific questions. Generally, can AI help with monotonicity formulas? There's lots of different monotonicity formulas for different equations. Can it do that? And even the art of the a priori estimate, can it start proving a priori estimates? Like you have a lot of different things, and can we teach it that? And so I suppose a lot of things I'm saying about Ricci flow could be said about any subject in AI. But it's a remarkable subject. And so far, it's been remarkably effective. things have not got out of hand, and hopefully that will be true in 4D. But maybe that's something for humans and AI to discover together. And here are just some references. And I think maybe I better just stop there and keep it at that. Yeah, thank you.